series into marine energy composites and manufacturing. Thanks again. I just want to introduce myself. My name is Bernadette Hernandez Sanchez, and I'm with Sandia National Laboratories and helping to understand how materials and coatings could be used for marine renewable energy. I like to go ahead and introduce our seminar series. So next slide, please. So far, we've had a series of seminars that started. Last week, we went into understanding and learning about crevice corrosion from Francisco Presuel Moreno from Florida Atlantic University. Today, we continue to learn more about our investigations, and we're going to go over some of the results with Professor David Miller on our summary of marine hydrokinetic energy composites testing at Montana State University. I also like to invite you to our next series, which will be understanding about some additive manufacturing work that's being conducted at NREL, and that'll happen and take place on April 9th. And also like to invite you to come and attend our Marine Energy Composites and Manufacturing Workshop that will happen on April 16th. So we hope to see you there. Today, we're going to be recording this event and also ask that if you can, during the seminar, if you have any questions, please feel free to add them to the chat session, and then we'll answer those at the end of today's seminar. Next slide, please. And just to give you guys a brief overview on how this work all fits into the current work that's going on to help the Marine Renewable Energy Program. Just this slide just gives you a couple of bullets on how this work fits into our foundational and cross-cutting R&D. We've spent some time to really try to understand the environmental effects and loads on composites. We're trying to really make sure that in our experimental results and experiments that we're really trying to make sure that we're making the connection between the experimental designs and the actual MHK conditions that are being used. We're working on standardization methods for some of our biofouling and characterization. And also we're really trying to make those connections and understanding not just the composite behavior, but the material science, and really looking at how the effects of corrosion, biofouling, and load are all being tied in. So with that, I'm going to go ahead and stop there. I'd like to introduce you to Professor David Miller. David and I have been working together on understanding these areas for quite some time now. And he is a professor from the Department of Mechanical and Industrial Engineering from Montana State University. So David, thank you so much for joining us today and sharing with us this research. I'll go ahead and I'll let you take it away, but if you could go ahead and also introduce how we got some of these materials too, that would be great. Thanks. Bye-bye.
Yeah. Okay, thanks everybody. So go ahead and put your comments in the chat, and we'll get to those at the end. So like Bernie said, I've got a lot of work here to talk about. I'm going to fly through a bunch of the results and not get into the nitty-gritty of the results, and just kind of show you the depth and the breadth. All of this is captured in a 5-year report that we put together recently. But this is a summary of kind of where we've been and where we from the ground up, where we started in the MHK composites world. So really going to talk you through 4 different presentations, work through 4 different talks here. The effect of moisture uptake on the effect of stresses. A second will be damage development, propagation. Third, different fiber angles and layup sequences and the effect of how that can change your process. Then last one, the strength reduction. This is the last kind of report that we put out. Where we opened up and got a bunch of samples from industry, from maybe some of you who are listening. I don't see the list of attendees right now, but a lot of coupons that were brought in. We ran them through the same type of tests that we've been doing in the previous studies, and go through there. So like I said, I'm going to present a lot of data. Kathleen's really worried about the number of slides. I'm not going to talk about every slide to the level, and just kind of show you the kinds of data that we have And if we can get through this pretty quickly and point you towards this paper that's out on the Sandia's webpage, or the theses that these students worked with to put us in. So problem definition, how did we start, right? Where do we understand the composites and how these systems are going to be in the water and what the uptake is going to be? We know that the structure is going to have stresses in it and so as the stress develops while the moisture is uptake. So this is the first kinds of things we really started to look at, and looking at the effects of the moisture distribution to try to get an understanding of that. Understanding that this is a diffusion-based process, right? This Fickian curve. A couple of things to look at of this. So when you look at these types of things, you'll see this data presented by us in multiple times. So moisture content on the left. So how much moisture, how much weight gain is being brought into the composite, the plastic. If you put this in the right basis down here. This first section up here, this is a linear line. We call that the diffusion, the diffusivity. And then where this asymptotes out, we refer to this as an M infinity. So the pure epoxy systems is, the M infinity, the total mass uptake would be 2.5 to 3.5%. And that's just a ballpark number. The chemistry does affect this tremendously, as well as other things going into there. But as a engineer looking at the diffusivity will tell you how long will it take to get to water to affect certain areas, and the M infinity will tell you how much mass and how much the kinetics of my part, the density of my part may change once it's fully there. So what I just kind of talked about, diffusivity, if you can calculate this out in an experimental calculation with these types of geometries, push this part out. We'll want to point out that one of the things we first looked at too was temperature effects and hydrostatic pressure, right? So is the curve on the bottom right here, so the diffusivity is really, and the max content are really not affected by the hydrostatic pressure, and it's a pressure gradient issue. We can talk about that a long time. Then the other part is the temperature and the rate of diffusivity at different temperatures. So one of the things that we will talk about is when we soak our parts, we actually do use an above ambient temperature just so we can get it done in a timely fashion. So it's an accelerated aging process. So one of the in this initial work, looking at the free volume, where spaces go, what space exists, and why this is important, because when I stress it, this free volume changes, and this is explained in other parts, right? So the volumetric strain of a plastic part is also affected by the amount of matrix and fiber and how all of those are oriented together. And so you can look at the volumetric strain due to the stress, the volume fraction, the fiber content, the fiber angles, all of this is affected in that free volume, right? And it also affects the max moisture content, how much that comes up into. And so, which also changes the diffusivity. And so here we go. So, right, so this is not new work for us, or this is us recreating and applying theories and things that have already been done. But looking at, back with Springer in '76, we really kind of started all of this work, right? And so changes in the diffusion parameters and how all of this can be affected by volumetric stress. And so continuing that on, right? And so what we know that the applied stress, because we apply it, we know the fiber angle, we know the volume fraction, we know all of our densities. And so now looking at the different systems with this can we predict this, right? So one of the initial early on, and this was I don't know, probably 10 years ago now. This is a 5-year report, but some of this work really started a long time ago. And so we were looking at how can we model how the water diffusion and then the damage to degradation in my structure along with that, and can I put that into a finite element analysis? And so we used a thermal analog system to still do that with ANSYS, and we're able to find out that we could model these systems and come through, and we could watch the diffusion grow in through the part. And so we were successfully able to do those kinds of movies and look at and do this on an experimental part, which then could be taken into a structure, and you could do the same thing on any type of structure and look at where my uptake is coming in, and then degrade my strength properties affiliated with that. And so you can look at different times and nice little properties that FEA enables us to do 1D, 2D types of systems. The question is how good was that in the process? And this is just kind of our process of how we related the temperatures back to diffusions and mass uptakes. And so experimentally, we went through a process to now build different types of fabrics. We used a stitch Certex glass fiber system and built coupons, and then we put them under stress. So we built them at different angles, applied different levels of stress. This with the springs, that if someone's going to ask, it wasn't necessarily a constant stress problem all the way through. Yeah, that is really true. But we did come through and calculate stresses and drill the holes in the locations to get the right deformation into the springs after we characterize the spring stiffness and those types of systems. So what that turns into and what that data output is or something like this. And so cumulative plot up on the left, and you look at, right, so the change in weight for all of the coupons. And so if you break them out into different applied stress levels, so upper right, so a 0 MPa. So this is just what we typically have done, right? So under no level, no stress at all the 0, the 20s, the 45s, and the 90s all overlay on top of each other, which is what you would expect, that there's no effect of the angle on the uptake curve. So now, but when we start to apply even low levels of stress, 18 MPa, 30 MPa, by no means really stressing the part considerably. But now if you look at a 0-degree coupon to a 90-degree coupon, you're starting to see a change in the diffusivity, change in diffusivity and change in M infinity. So more mass is uptake or is absorbed into the part. And if you look at this on the 30 MPa, we actually you have some guesses here, just some notional type of plots to kind of to fill this out. These coupons actually broke. They could not take the amount of stress that long. But even at the 30, you can see the growth and the change and the increased mass while under a tensile value. And going from 0 to 90, right? The whole reason for that is I am stressing the matrix more. So the more that the matrix is stressed, the larger the free volume, the more mass can fuse into that free volume and increase more. So while a lot of numbers, and you go, well, at a static condition, I'm going to have a different I'm an M infinity for a matrix material, but under stress, under even minor stresses, that M infinity can significantly increase to a different value. And that's worth noting, and something, if you're looking at a dynamic part that is moving, has kinetic processes, knowing what the mass property are can be a big deal. All right, so this continues on, and this is the just the linear portion of that diffusivity. And so you can also see that the diffusivity changes for this 90°. So going in from a for different stress levels, right? So that's just telling you that it will get to highest level faster than it will at a 0° system. So fractures, a lot of the parts ended up, like I said, some of these fractured along the way, and very unfortunate parts of being able to track this data. But you could see the damage that occurred and looking at those systems. So comparing the theory and the experiment on these systems, we were able to come back and look at how we could model, how our ANSYS model was able to capture the experiments. And so we feel that our analog system and the temperature analog inside ANSYS allows us to be able to capture these systems well, as even with the off angles and applied stresses. So diffusivity values, the process, and you can go through the equations later. Not a whole lot of equations in this talk, but there's some. But then the same kind of concept of, can the ANSYS also, is it capturing and is it using the same diffusivity types of analyses? So key observations and take homes from this work, right? So just that the magnitude of the diffusion changes, the diffusion parameters change from the 0 to the 90. So matrix loaded materials have significant changes in the M infinity as well as the diffusion. And so this will kind of be this will come back later here in the next 45 minutes of seeing other locations where how the stacking also affects the overall strength of my composite because of what I put in my outer layers and outer plies. So we consider that we were able to successfully capture the experiments, capture them into an FEA type of system that could then further be utilized by an engineering system, engineers trying to do analysis on these systems. Okay, so moving to the next one. So looking at the effect of hydrothermal aging and what does that do for the damage progression. So as similar kinds of things, right? Moisture-induced swelling is the challenge in this one and what we were really looking for. And we're bringing in some different types of analyses to look at these types of systems, right? And the basic one is the acoustic emission. And so we delved into the process of AE and lots of our research around here, and really looking at, can we use that to identify when damage is occurring, how much damage is occurring, what the damage is, and looking at just the types of events and what in a dry or an absorbed in a dry coupon, what are the differences in those? So inside of this, I'm not going to make you an AE expert in this talk, but what ends up happening is it's a microphone. And if you've ever tested composites or played with composites, you've bent them and you've heard them pop. Well, that pop is a noise, is a sound that travels through the coupon. We have very particular, very specific microphones are listening to that, and the microphone turns that noise into a voltage time signal, right? It looks something like this. And so we are reading this and listening to it, and there's a bunch of data that we can pull off of this. If you're a double E, it's just a chirp kind of part. So, but there's energy that's under this, and you can kind of see the blue curve, the peak frequency. What is the frequency of all of these parts duration, rise time, et cetera, and lots of different processes in that. And again, the acoustic emission world is very in depth, and there are specialists who spend their career on this. And we were users of the technique and trying to develop understanding of our material using acoustic emission. So in that, right, and so this is kind of a graphic we put together that kind of explains the AE world out there, right, and what they're looking for. You know, so you have you have damage that happens in one form or another, right? These different types of different processes, they have a wave, all right, and then we measure that wave, and we can pull certain things out of that data, right? And then we can look at that, and you can analyze that data in multiple ways. One is just a number, right? A single parameter method. Let's pull a number off of that chirp and see what we can find. And then there's multiple parameter methods. There's neural networks, clustering, waveform, wavelet types of things. All of those things can be done. But again, the ultimate goal is to identify the damage that's occurred, severity, predict life damage, those kinds of things. So the single parameter models, this is kind of, again, just pointing out things for you here, not necessarily MHK related, but so just we're looking at if we measure certain things, so the frequency that comes out, researchers have tried to characterize a specific frequency measured to a damage mechanism. So, and that has been done by quite a few people, and this top group is kind of our analysis of that and where we put those into the types. So AE is right. So it's still it's a technique that can aid in the understanding of the effects, right? Indirect measure, you know, and can we change and can we look at these types of things? So what we really have done is in this work, now that everyone here has heard a little bit of acoustic emission, I guess. So what this work really did is now looking at the diffusion of the swelling and what happens with the damage, just the damage that occurs without applied loads, right? So what is happening, just what kind of damage is being produced with that? And so we had some control coupons that we aged, right? And so you can kind of see here where we point out that, right, we distilled them in 50-degree water for accelerated aging. And then we would age them and then dry them. And so what you're going to see here is a set of data where we took control coupons, we accelerated aged them in water at elevated temperature, put them back in the oven, dried them back out, and we also had some that we just left in the oven without the water. And we'll talk a little bit about that as well. So you can see a lot of this data. And this is out of a DSC, so we're looking at the change in the glass transition. So this is really just a matrix question. So you look at a TG from a control, you add the water, you age it, it lowers the TG, you dry it back out, and the TG goes back up. So we also did swelling, right? So looking at the time the soaked and mass uptake, so a linear mass uptake. And what we were able to measure off of these coupons was the amount of swelling and get a number, a beta number, so a swelling number for this particular resin with this particular post-cure. And we were able to measure and generate those parts, right? But also with that, you can start to see, right, what the coupon starts to look like originally, and then after it's soaked and after it's aged for a long time, you can start to see these swelling induced cracks inside the material and the matrix part. Just a really good set of work by this student. Again, so here just characterization results of what the moisture uptake looks like. You see a couple of layups here. So the 090s and the 90 zeros, zeros and 90s individually. Looking at these, desorption results. And so after we bake them off, how much does the water come out? And so interesting kinds of things after you just looked at this and you control it and you age it, you can start to see a change just in the material, just in transmitted light. So just looking at the part, you can see that the damage is occurring and has started to occur just from soaking inside the water. Slice and dice it and polish it up, and it looks real pretty, and you can see the cracks start to develop, and you can identify various parts within the crack or within the coupon of what these cracks look like just from the hygrothermal damage, right? And so more pictures of those just to kind of keep that going. So here's some stress results. So again, just look at the parts. So dry controlled, saturated, dry desorbed, right? And dry temperature only. So again, trying to make sure that our accelerated aging, just stick it in the oven doesn't change it very much. And if you look at the 0s and 90s out here, you look at these coupons, a little bit of change, maybe a post-cure effect here, but from the dry control and the baked control at you see very little difference there. But if you come back to the dry control to the saturated, there's a significant drop in ultimate stress for each individual layup. You see that, and then when you dry it out, right? So the question that this is really trying to answer was looking at is the drop due to the water being there, or is the drop due to damage that the water left behind and left as it soaked through? And what this data is really is showing you is that and is demonstrating, in our opinion, that is just leaving a wreck behind. It's not about the water being there. It is the damage that the water swelling does to it, and this is proven out in this work. So if you look at ultimate loads, and this we can go into this and other types of systems and reasons why, but modulus changes, there's really not much modulus change. And so this is a tensile modulus of these parts. So one of the questions, if in composite theory, I have damage would change. Does it change the modulus? In metals, a plastic strain still doesn't. But if you look at it in terms of a applied discount type of just elementary model processing, you really don't see that kind of change in the elastic modulus the way that theories sometimes project. If you just look at a stress strain curve rather than just a number of ultimate stress. So other things that really jump out at you is just looking at the curve, right? And so we're going from the black is the dry to the wet to the desorbed, and looking at the process and model of these. So this is a 90 transverse coupon, and you can see the drop of where that knee is. And by just pulling out a single value of going, what's the ultimate stress? Well, the ultimate stress is, the in spot on these curves, not really what happens and evolves through the process. And this really demonstrates way more than what a single value is. And so as an engineer, as a professor, you always make the students go back and plot the stress strain, because it really tells you the story. In the 0s, you really don't see as much of that change type of process. In the plies, a little bit, you can see kind of the change from the initial linearity part, and this is a more damage tolerant system than the other parts. So when you look at this, the coupons themselves, right, really kind of are going to demonstrate some of the issues of why and what's being seen in the damage propagation. So we'll start here on the left. So these are in opposite orders, but so dry in the middle, saturated at the top. So dry in the middle, you start to see a lot of cracks develop in the process and moving through these coupons, right? So it's more damage tolerant, and so it gets before ultimate failure. In the saturated part, you don't see as many of those cracks going through before ultimate failure occurred. In the desorbed, you see a lot more of those same type of thing. So the damage mechanisms due to from the dry to the saturated is fairly strong. And the same kind of thing in the cross-ply systems, where you can see in the dry part up here, you can see the widespread delamination across the whole coupon. And so just the whole process of how the part gets from beginning to end is very typical. So in the saturated parts, what you end up seeing is you don't see the widespread part. You just have a very localized spot that gives way and goes. So again, looking at multiple types of systems, you look at the dry part. When you have the zeros on the outside, you have the big fiber brooming and the large failure process, what you're used to, or what we're used to in seeing composites fail. In the saturated part, that doesn't happen, and you see just a very localized damage that drives ultimate failure. And so interesting things that come through here. This is actually probably the first set of acoustic emission results and what this really looks like. So looking at energy, and these are frequencies. So each frequency, each dot represents an event, a damage event that is measured in the coupon. And so, and what you can see is that the banding, and where I talked about different frequency bands to different damage mechanisms, we start to look at how these frequencies, where these frequencies occur, and how the process goes through there. And so what that enables us to do is go through and look at where the damage initiation occurs. There's a lot of data here, and you can plot this up in many ways to help tell your story and understand how the mechanisms and damage progression works. So lots of this type of work going through, whether it's where the initiation first starts, where does the first strain, where does it first start failing internally, and so lots of work. So the conclusion kinds of things here, right? These are broad stroke things, right? So strength and damage reduction and the processes on all the way through. AE behavior changes, and what more than anything, rather than just saying the strength lowers, the whole damage process changes. So the damage tolerance and the damage evolution of the coupon is very different. So your part that you're going to build is going to not just have a reduced strength, but also have a reduced damage tolerance and process all the way through that. Okay, so about halfway through, so looking good. The next one, looking at a couple of other parts on this, off-axis fiberglass systems. And so really starting off so now looking at, this was us looking at the acoustic emission parts and trying to understand the effect of the angles on the mechanisms of failure. So looking at pure off-axis, unidirectional off-axis at 15, 30, 45, and then cross-plies at 15, 30, and 45. And so doing dry and saturated parts and comparing those systems. And then also looking at other sets of data here where we are looking at zeros and 90s, so 0, 90 symmetric, so 0, 90, 90, 0. So we have a coupon with a 0 on the outside and coupons with 90 on the outside, so 90, 0, 0, 90. So how does that change the process, and how does that go through? How does my understanding as an engineer of how I put my ply stacking together do I do it different for an MHK system because of the physics that's going on, that it's going to be in? Um, so again, kind of things we pointed out before. When you put these in here and you soak them, you can start to see visible damage inside the coupons. And again here, so all the way through the unis off axis and then the cross plies off axis. The unis show a drop, but not a significant drop. The cross plies show a larger percent drop in static strength. And so where we take this and where the process ends up going is, right, so if it's a shear driven failure, is it a interface driven failure? Various processes with that and looking at those kinds of things. And so we're using the acoustic emission process to look at how does it change for each mechanism, and does it start to move between a matrix cracking type of process or to a debond, and that's what basically what we're seeing is that in these cross plies, that soaking it changes the damage mechanism from a cracking to a debond or from a debond to a cracking. And so you can see this large shift in process for each one of those types of mechanisms all the way through. And that data is described in the paper and several other conference proceedings and thesis, and Jake Nunemaker's thesis, and you can go read about that and would certainly take questions on that as well. But a lot of data there that you can come back and through. You can go back and go through, but really just kind of understand the process that, what we're trying to do is understand the total damage mechanisms. And again, I'm looking at the stress strain curve. So this is just a unidirectional system, and how the strain, what the stress strain looks like, rather than just pulling off a max strain, max stress value, a strain value. That the evolution of this really does matter. Okay, so partial saturation, the last part of this work is pretty simple, but it is key in a few things here. So it's just changing the stacking sequence, 090, 090, 90, 0 to a 90, 0, 0, 90. So from a pure, right, neat coupons, right, should all start at the same, right? And then where they end at full mass uptake is pretty near the same, right? But what happens in between, right? So this is more of, when do I need to understand the failure in my part? And so what this data, we were able to show with this data, is that if I have my 90s on the outside, I can absorb more stress but still maintain the strength, because my zeros my main load carrying fibers are not being degraded as fast. Where when you throw this into the zeros on the outside, the diffusion is the swelling is coming in and damaging those parts, and I see a faster reduction of the material, and so it does have so stacking sequence does have an implication, and so really key point here: acoustic emission analysis, a change in damage progression in the process. And so some of this is changing the progression, matrix cracking prior to interface damage. So conclusions of the process of understanding and things that we learned about what the water uptake does to the specific parts. So we'll go back to there. And so the last talk, last set of work we'll go through is hydrothermal aging on, again, same kinds of things. So in these coupons, all right, so again, looking at the implementation parts and still focusing on the single parameter systems and identifying the damage. So what's different in this set of work, and you'll get to here in a second, is, we'll just go straight to it, is the materials that we set. So the basic research that we were doing was captured in repeating what was done in previous studies. What's different is we opened it up to, like I said, maybe to some of you who are out listening to this, to a whole different set of coupons and of material sets and fabric sets that we hadn't really experienced a lot of. So a lot of different types of layups, right? So looking at, and these were all provided to us as coupons. We didn't make any of these ourselves. So you're looking at different resin systems, you're looking at different fabric systems, and you're looking at different layup systems, and presented from, so just fiberglass. We have fabrics, hybrids that were glass and carbons, and we also had some helium resin systems, and we also had some thermoplastic parts, some HDPEs, polypropylene, nylons, and systems that were given to us in biaxial parts. And so again, so this last part was in the MHK program, where we reached out rather than MSU and Sandia picking the materials and looking at the science part of it. Is, well, what if we open this up and take our science, the science and engineering testing that we've done, and apply those to your sets of work and your sets of materials that are of interest to you? What does that end up looking like? So this was a reach out to industry, and this is where we got. Certainly it could be a lot more. So in the thermoplastics, right? So large volume, large mass gains, right? And some of these, up to 6 to 7% mass uptake. Some of these are starting to lose some mass on the back end. And you can go through and pick out these numbers and what all of these are in the other work. But anyway, so look, very different types of numbers than what we were seeing and what you typically see in the epoxies and vinyl esters and the thermoset systems that are down here in this 1 to 2 range. So very large different stuff. So even here, and some of these thermosets, right, are in the 1 to not even to the 1 range. So mass uptake processes that you've seen us do before. Carbon glass systems, we had coupons given to us in those ranges, and so you have a lot of different physics here that we really didn't delve into. It's just kind of repeating, turning the crank on the process. These would be really interesting to get into, where the swelling issues and how the uptake in the glass, or uptake in the carbon, and how that is changing your uptake as well. But not quite what we were getting into. So we tested these, and so you can start to see the processes and how all of what the coupons look and how they come out of water, and they don't come out looking as pretty. None of us do, I guess, if you had to say it that way. And so the thermoplastics parts, looking at the processes of those as well, you can start to see the damage coming out on the top one, and all the way through. So some of these are you can see the fibers pulling out through here, and some of these just have a straight break. Lots of different processes here, lots of different coupons going from very large, high energy failures that you see here on the bottom with the brooming parts, to some of the other systems where you can see the nice damage sets and leading to ultimate failure. All of this is captured in multiple sets of the paper, the 5-year paper or thesis, and PComps and Sampian Mechanics papers as well. So, so with all of these tests, you're looking at, if you want to boil this down to a number, what's the number? Well, some of the numbers are modulus, right? And so if you look at some of these sets, one of the things that really kind of jumps out at you is there's really not that many of them that have a significant change. And so it kind of similar to what we talked about earlier in the hour is there's not a significant change in modulus. Sometimes there is. Sometimes it's just coupon variability. But if we look at stress values, I would say if you were to look through these numbers, one of the things that may jump out at you is the blue number, which is the unconditioned. So the dry number, the first number is always higher than the second. And so, the volume or maybe the volume, the value of that drop is not super consistent. Thermoplastics down here on to the right, that some of the coupons here, and we talk about this in the paper. One of the things, these are thermo sets, but one of the things that you just kind of jump out at you is this, where these values are significantly lower than the 6, 7 C1s and the C series. That this is really there were some manufacturing issues and defects into the coupon at the very beginning. And so what we say in the testing business, if you start with you start with flawed material, that water and other damage doesn't really change it that much. And so that was really kind of borne out in these tests for us. Failure strain, kind of same kinds of things. Just do not failure strain also changes and drops for almost every coupon across the set. If you look at, and so see where we're at. So, right. So the thermoplastics had the higher diffusion constants, larger volumes. We saw more than in those types of systems. Thermosets lost work, lost some of the mass there at the end. So then other sets is to look at and jumping out a few of these other parts. Let's see where are we at time-wise. Probably I'll just go ahead and run through a couple of these real fast. Again, similar kinds of modulus, strength, and failure strain, looking at glass and carbon systems. And we'll throw that out there and end this at 11:50. I think that's about where we're at. So moduli generally unaffected by the moisture, strength of failure generally decrease, low quality laminates are affected less. So with that, so what did I just throw at you? I threw at you 5 to 8 years worth of research of coupon data and science and engineering on a wide range of coupons, trying to understand what the mechanisms and what the processes are of those general systems. So with that, 11:59, I will open the chat and open to questions, I guess. How's that? I can stop sharing. Where do we? Okay. So I see two chat questions. If anybody else has any more, feel free. How frequent do local high C states impact MHK structures? As a non-MHK developer, I think somebody else could probably answer that better. But I would answer that as a designer. I have to design for them to be able to do that. As a proof load, not as a fatigue load at those high levels. But so how frequently that I don't know. Sorry. As the designer I'm trying to understand what do I need to account for, I would say that's really why we're doing this. What are the opportunities for small business that are fluent in data analysis to collaborate? I think that's a great question as well. As an education institution, I'm always interested to collaborate. What your processes might be. Um, Look at the Q&A below. So what am I missing, Bernie?
There's some questions about your presentation, and also a question on which samples should they use? Which type of material should they use?
I
Do
don't
you
see
see it
any. Yeah, I don't
on
see anything
Q&A?
else in a chat.
It's on the Q&A below the chat.
I don't know. Okay, I can't Q&A. Let's look at that one. Okay, that's a different window. I have not pulled up those. Sorry. Thanks. Will they made? Hey, Jed. Yep, we'll put them out. Some of these are yours. When looking at the damage due to moisture absorption, did the vinyl ester do better than the epoxy? All were untoughened epoxies. Generally, the deal with the vinyl esters, I would say overall, yeah. I if I had to say yes or no, I would say the vinyl esters definitely have been controlled to absorb less, and so that changes that changes your beta, that changes the damage states of into that, um, and so yeah, and Jarlath, good question. I think the one you're using it looked really good actually. The CE series of the hybrid systems, I think, were the best systems that we've tested that were out there. So I think you guys have kind of honed in on a good set. So does that help? So I think that's the $1 million question is which one do we choose? To put on our Sandia hat and DOE hat is we're not here to pick winners. And so, but I think the systems that you guys have been implementing have generated good data sets from us. And I would say I would feel confident with continuing on the way you're going. So, anybody else? Where's the link to the paper? Oh, that's a good one. Hey, Bernie, could you put that in the chat?
Yes, I'll try. I also, for those of you who got a friendly reminder, there was a link in the emails that went out that says Sandia releases report. But let me see if this works. It looks like the link just gives it's not showing the link, but I will send that out as well. So Jed has another question. What are the options for future work?
Ooh, uh, that's a good question. Um, I guess the main question would be where the program itself goes and how well we can open up to more to different material systems. And we put together a proposal to go to DOE and how DOE approaches this. We would love to continue this work on and look at this. I in the one-off kind of systems, I think there's probably processes where we could get into the testing and understanding of it. Whether you want to do that as a, the way we've always done this with the wind side is any companies who want to get involved with it and have some questions that can throw it into the materials program. If you're willing for that data to be public, then we can do a lot of that work within the program, within the MHK materials program. If you don't want it to be public, then we probably need to take that conversation offline. And so that would be the process. We are pushing, we're at the end of one program trying to start up the next. And I think that mantra of testing materials that companies are interested in and making that data public, it is still always forefront for me. Data just doesn't exist for this, right? And companies don't present the data in ways that an engineer needs them or wants them. And hopefully we can still continue that that process. Hey, Peter. Like I said, you can't see that. Does that help, Jed? I mean, hopefully we'll know more very soon of where our materials program is going to go. Yeah, I would absolutely say that. I would agree, Peter. The one of the processes with this of the coupons, why some were lower than others, would be, we tested what we got. Hate to say it, make it sound that way, but we really weren't looking for the optimized kind of value. This was put out to manufacturers, to materials manufacturers. Hey, we can get you some data on this if you're interested, and you can send us some material with that. So I would say that the systems that were tested were probably not the most optimal systems that you would investigate for MHK types of parts. Probably not. If I had started down a material selection path and wanted to include thermoplastics, I'm not sure these mechanisms and these processes were the ones that would have, no pun, yeah, pun intended, would not have floated to the top. So any opportunity, the NIST system, I think, is a great parallel that DOE could look at. We continued on what we put in so far, and I don't think there's anything directly comparable to that infrastructure program, Jed. I think the material sets that can come out of that or will come out of that will have very relevant systems to this, right? You're going to have to answer the aging, the environment, the types of questions that are going to go into the infrastructure type of composites are very, very relevant to these material systems. Thanks, Peter.
So yeah, just quickly, there was some questions about some other future potential mechanisms. These can include FOAs, SBRO topics, and other technical assistance that we could definitely look into as well that are available to us to collaborate a little bit further. Also, we're getting to our time, so I'd like to say thank you so much to everybody attending, and we hope you can attend our next seminar series as well as our upcoming workshop. Thank you again.